Okay, so now we'll do the Appendix A. So I will just give some necessary facts for the projective abelian group action on some convex domains. And so in A11, we do the so the free abelian group actually decompose the space into some joins. And so in A12, we'll talk about the convex projective with orbifold free abelian groups, and we will show some decomposition similar to the divisible projective action in the for the abelian group case. So these are not properly convex, and then so on. Okay, so the first part is A1 is um, so right now did some similar work, but she doesn't work on the co-compact action. It was more on the end theory. Okay. I don't think I need these. I will drop this later. But anyway, so the first lemma is, so suppose you have some representation with the unipolar elements, and so if these are generators, then actually you can find the positive diagonal representation with approximating these under any epsilon. So we can actually find the continuous parameter so that this is positive diagonalizable. So so the first of all, what we do is we try to do it with uh, f r1, so n equal to 2 case, and then so these are the units. So you can assume that these are all abelian, so you can push it into upper triangular matrices. Okay. So for the abelian, so you can put this into FR1, and these are given like this, and so commutativity will be reduced to this. So the really solution will just be given by this. Given any B1, you can get anything else by just this formula. Okay. So when you perturb it to the 2 by 2 matrix with diagonal AI, which is very close, AI and 1 over AI. Okay. Um. So you suppose you can do it for k minus 1 dimension, then you can do it for k. So you have some unipotent homomorphism like this. Okay. And then so these are, you can conjugate, so it's upper triangular, and so you denote these k minus 1, k minus 1 matrix to be the upper left one. So these are still upper triangular. So by induction hypothesis, you can approximate these ones, okay, up to epsilon minus 1. And so in general, you can perturb these to this with some changes in lambda here. So we need to solve for this b prime 1, b prime z, to give a bi, and so the equation to solve is actually this. So for commutativity, so you write this mi to be this, and so mi mj is mj mi. So I wrote this wrong in the previous version, but the solution is just this. So the mgi, you just need to multiply by inverse, and then you get everything here. So that's the solution. Okay, so then so you can generalize to one higher dimension. That's the idea. So if L is a connected projective abelian group acting on a properly convex domain co-compactly and faithfully, and then L is actually positive diagonal and the domain is simplex. So if it's properly convex domain, then it is simplex. So that's because then you did X properly discontinuously, so you can just apply the Penua theorem, and then that's the idea. And so because it's connected, and because you right, it's connected, so you can take a co-compact lattice here. Okay. Um. Uh, Right. I think I need the free abelian group here, but maybe I don't. But anyway, so keep going. Okay. So that's the idea. And then you have any G in A, then the minimal polynomial is always like this over the complex. So you can write it in the real form like this. Okay, so this R is the real part. And you can now write the primary decomposition space as this for lambda I real, and then all this one. Okay, or these polynomials. Okay, so so if G is a non-identity element, so the primary decomposition space will satisfy this for any H commuting with G, and for any primary decomposition space of G and then H, C intersect G are both invariant as long as they commute with each other. Okay, so these are both invariant. These things, and so if you have a free abelian group finite length, there's a maximal collection like this, which direct sum is this, and each Cj is G invariant in the primary decomposition space of every G in A. Okay. Okay, so these are just some facts I is following from some textbook, so I don't want to go through it. So so the scalar group is some group like this, and the scalar unipotent group is some product of scalar group with unipotent group. So a subgroup of a product like this, and so for each A bar Ci scalar unipotent group for each I. Okay. So for this Ci, if you restrict this A, then it will be a scalar unipotent group if you decompose like this, because it has only one eigenvalue there. Okay, and so if A is a connected free abelian group acting with positive eigenvalue, then there is a decomposition where AI is positive diagonal group on A0, B0. So B0 is where all these Ci has dimension 1, and then the rest is some positive access positive scalar unipotent group for each Bi. Okay. So just look at these Ci's and then you restrict it and you get these kind of things. So suppose that A is a discrete free abelian group whose Zariski closure is A. So if elements of gamma has only positive eigenvalues, then um, A mod gamma is actually compact. So I guess I should say it's projective group. So I forgot that. So the proof is just that you use this previous lemma, and then there's this decomposition, and if you do the Zariski closure for each restriction, then it is a unipotent group here, up to scalar. So unipotent group always has some Zariski closure so that it is called compact. The quotient is called compact. Okay, and right. So AI should be the connected Zariski closure group. Okay. So then this gamma and AI will be some subgroup of this product group times Q. So Q is a diagonalizable group acting trivially on this, acting diagonally on here. Also, I can say it's also trivially here, but so since AI is or abelian, must be free by unipotent. So A is again a free abelian group, and so let's look at all these eigenvalues for each one of them, and the D is acting as scalar group on this and positive diagonals here. And so we can find the homomorphism C to D, sending D to the tuples of just these eigenvalues. And so gamma will have a co-compact image on the C because CA is connected diagonalizer group in Zariski closure of this. Okay, so these are just or you can think of this as C as diagonalizer group. So these are all going to be nice, and then the Zariski the co-compact the group will be co-compact on this Zariski closure. Okay, and Right. So if you take the corner of this group, then this is a unipotent group containing this, and so it's Zariski closure. So also is normalized by gamma. So it's a proper subgroup. So there's an actually is a smaller thing. So this means that this is actually co-compact in K. Okay. Right. So what I wanted to show was this was co-compact. So you cannot have anything mapping to smaller group and be a smaller. So if this unipotent group was any smaller, you cannot do this. Okay, so that's the proof here, and the so A12 is so A16 is if you gamma is finite generate pre-abelian group acting on this co-compact domain properly and co-compactly, and then the Zariski closure of each finite index subgroup is so that L is compact, this is co-compact, and L has only passive eigenvalues, and omega is actually orbit of this abelian group L, and then omega is a join of these for the complete affine spaces, and pi the point, and these are all independent spaces, and this contains a central Lie group the rank p plus q minus 1 trivially on each of these and pk here. Right. So the proof is that when omega is in Sm minus 1, if it's properly convex, then this falls into that case. So say omega is not properly convex, then also first we show that gamma is no invariant lower dimensional space meeting omega, since otherwise it's X properly, so that it is virtually homeomorphic to lower dimensional manifold homotopy equivalent to cover of this. So that's a contradiction. Okay. So there's no lower dimensional subspace meeting this in the interior. Okay. So the positivity will be proved. So if you have these C1 CPQ obtained as in lemma, the previous lemma, and we can also write like this. So these are the eigenvalues associated with these things. And let's say C hat J to be one which you drop one of them, J is one. And uh, uh, you show that this omega and S any of these Sj hat is empty, so you can project this to Cj. Okay. For P plus Q. Okay. And so this omega j is image, and we can show it's convex subset because it's an image of convex subset. But also it is also in a hemisphere, contained in a hemisphere. And the reason is if it's not true, then this means it goes onto this space. And then you can find a pair of antipodal points. I mean, pair of segments connecting point which passes some CJ hat. But this doesn't meet that, so it's contained in the hemisphere. Okay, so now we consider action of gamma on CJ with only eigenvalue equal to 1 by just multiplying by some holonomy homomorphism. I mean the homomorphism like this. So these will be now also potent. And then so there's also potent flag in Sj, and there is hence a proper gamma invariant subspace. And so you restrict this gamma to gamma j, and the gamma j is again abelian, and there's a unipotent lattice. So this will be also free abelian. So unipotent lattice in the Zariski closure of this. So this is discrete. So this shows that this is also virtually unipotent, and so it's a Zariski closure. So gamma j is actually virtually unipotent. You can prove that, and so you can take the inverse of these, and then you get a finite index subgroup of gamma with only positive eigenvalue. So the Zariski closure is of this is homeomorphic to these. Okay. So these are virtual unipotent. So there's a unipotent group here, and then so you can take the intersection of the inverse images. So these are just now going to be all just unipotent. So um, right, up to scalar. So this should be scalar unipotent group. So these will be only positive eigenvalue here. So these so if you have only positive eigenvalue and it's unipotent, then these will be all free the Zariski closure will be free abelian. Okay, and okay, so on. So now you can show that this is torsion free, and the Zariski closure is is in this for some diagonal group acting trivially here. So this is a closed manifold, and so this will be manifold. So this means that this has to be the same. Okay. So so once right. So this proves one. So one I showed that this has only positive eigenvalue, and this is go back so on. Okay. So for two, you just let gamma to be gamma prime above as above, and so if p equal to 1 or q equals 0, then this is just the convex domain in the affine space. And so this is going to be in omega is in some complete affine space. And this you can change this to be unipotent. And so then this acts as a affine transformation. And this is co-compact action. So in the proportion T of this, you can prove that actually this has to be special affine. Okay, so two so two follows from this spec. So if it's unipotent and has a co-compact action. And if p equal to bigger than one, then so omega cannot be complete affine, so otherwise it would be that. But it's properly convex. It's not properly convex either. So you get some sort of a projection. So there is some gray sphere here. So if you remove it, then there's a projection to this. And then you get this L1 acting on this image of omega. Okay, so this is properly convex. And then L is some corner. So L acts trivially on omega. I mean the omega 1. Okay. So by induction, this L1 will act transitively, okay, on this, and you can count the dimension, and then it will act on each affine space as a complete affine space. So again, this will be acting complete affine transitively by this lemma here. Okay, so. Okay, so those are the proof of two. Okay, so once you have this acting transitively and this acting, the L will act transitively. Okay. So I go to 4. So 4 is just again some argument about the existence of central D group. And these are just facts from the some because these are access some diagonal group in P0. So there you can obtain it from the Benoit theory, but if it's not properly convex, then you use a limit argument. So the basically this group is actually you can obtain it from these are positive eigenvalues, so you can obtain it from the diagonalizable ones. Okay, so in the diagonalizable one, there are always such groups. So you obtain these by the limit. Okay, so you can deform to always to diagonalizable one. So this will prove 4. And then 3 is that these are the join here, and so drawing part, you need to just work on these kind of limiting arguments that you can always push everything to these subspaces. Okay, so the projected image is actually the real image. So in the end, you can obtain these. Okay, so you need to work on the projection to these, and and then this really is realized. Okay, so so the next lemma is lemma 1.7. So lemma 8.17. So this is so if you have L acting on some space convex domain, which is in parameter. So this is a varying representation. And so suppose this given some continuous parameters homomorphisms, and this will then the point is that this actually converges geometrically. Okay, so the orbits will converge to orbit. So that's the basic point here. Okay, so the so basic idea is that it doesn't become a two orbit or three orbit or union of orbits because so we have this holonomy representation given as some sort of Lie group homomorphism. So HT is some Lie group homomorphism here. And the basic idea here is that so in the case sigma this T is always properly convex. I mean, of course, this limit will go inside an orbit. That's clear. But we will show that there's only one orbit. Okay, so the thing is that there is this group which I denoted by Q here, right? Okay, and then this group. So if you have more than two orbits, then there's some thing that the point in the where these two orbits are contained in, and this G will have largest norm there. And then the point is that as in the approximation, you can always get these balls again. Okay, so these are in the limit. So therefore they will intersect the previous orbits, approximate orbits. So then you can act by to show that it's not this gamma T was not properly convex. So this is contradiction. So it's not properly convex, and you can always project to make it properly convex, and then you can argue from there. Okay, so next is that if you have a mu is a real projective structure on cross orbifold with this developing map that's not injective, then any structure sufficiently close to it developing map is not injective. So the reason is if you have any 2 points open sets containing 2 points going there, then depth is embedding for each depth UI is embedding for each eye, and if you change it little, then the perturb from this you still have intersection, so therefore it's not injective. Okay, so it's sufficiently close case. So lemma 8.1.1 is that so if some real projective structure converges to U0 and then the U0 has goes into so depth 0 goes into some Zariski closure of some orbit of a Zariski closure. Okay, so component of so orbit of some identity component of the closure, then this will have to converge to that. Suppose that happens, then this step I will also go to the Zariski closure of the I mean the identity component of the Zariski closure of the corresponding holonomy group of this. Okay, so that's because this happened for depth 0, and this depth IT will converge to depth 0F, and so the orbit converges to orbit, so the fundamental domain will also go into the orbit. Okay, so and the orbits approximate, and the fundamental will also approximate, so therefore the orbit, this fundamental domain goes into orbit. So once it goes in there, then it has to develop in there. Okay. Okay, so that's the thing. And so mu zero is virtually deformable to properly convex domain if you can find the parameter of your projective structure of some finite cover so that this induced structure is properly convex for t bigger than zero. Okay. So you can deform up to some finite cover. Okay. So proposition A110 is that if you have a convex projective structure with virtually abelian fundamental holonomy group of finite of index, it is always virtually deformable to properly convex one. Okay. Okay, so you can just work with the GL as a fundamental group, and then this follows from my previous way of deforming. Okay, so that's how you can do it. And next lemma is that if you have some convex structure with virtual abelian fundamental group, so U is deformable to some continuous parameter, and uh, and then suppose satisfy that it is always virtually diagonalizable, or it generally acts on some properly convex domain, or it acts on a um, complete affine space, and with this DT has no proper invariant domain, then this mu T is always properly convex or complete affine. Okay. So this means that the properly convex and the complete affine together will form stable sort of situation here. Um, so basically, this is pretty long, and um, so the point is that if it's so you just need to show that everything goes into an orbit and the orbit converges, and the point is that so if it's more than one orbit, then the previous sort of this argument, this stuff will show that that cannot happen. So it always goes into one orbit, and the orbit converges. Okay, so that's the basic argument here. Okay, uh, and then for this lemma 8.112, so you have some properly convex structure for mu t, uh, then you can always write it like this as a join for a properly convex domain. And this is a span some subspace, and these actions are strongly reducible, and these are constant values. And so these are just essentially the idea of the Benoit. So you can just use Benoit theorem, and the continuity is also clear. Okay, so now we generalize this to this case. So we have some associated holonomy, and it acts on some properly convex domain or complete affine space. DT is a minimal HT invariant convex domain, and this is virtually if it's complete affine for at least one T0. Then sigma is always properly convex or complete affine for every T, right? So I should say Qt. So this is true for mu zero, but then uh, so properly convexity is only guaranteed at mu zero, but then this propagates, and so this step T is always diffeomorphism, and RT is uniformly bounded automorphism, and so if the sigma is properly convex, then all dt has to be properly convex. Okay. Okay. So then so if it's virtually abelian, then this is actually the previous proposition. If it's not virtually abelian, then dt is properly convex for all t by the premise. Okay, and then the set where it's properly convex is opened by the causal, and then you do the limit argument here. So then these things always will converge into some compact subset as you change, and then this has to be the into these things. Okay, so that's the theorem. And A14 is the final theorem here, and So the basically, so this summarizes everything so that if you have a path with the cube and then it's properly convex or complete affine at mu zero, and it acts on properly convex domain or complete affine space, it's minimal and it's complete affine point of this one t, then it's you assume it's virtually abelian. Then this depth and the holonomy will converge in the Hausdorff topology. And this is the same as Hausdorff metric topology, and the boundary also will converge in the Hausdorff metric topology in Sn. Okay, so it's always virtually uniform, immediately formal for properly convex structure. Okay, so everything is really proved here, but except that you just need to deal with the properly convex case, and that case is easy to prove using the geometric limits here. Okay, so the final thing is some justification for weak middle eigenvalue condition. So if it is n over 4, it's virtually abelian fundamental group. So if it has some sequence of properly convex structure or RPN structure, that with the generalized shaped, then if it limits to this, then this limit satisfies a weak middle eigenvalue condition. Okay, and so satisfy MP if it's MP and C or it's virtually abelian, and so the right. So I am concentrating what the virtually abelian fundamental group. So maybe I should drop this, right? Anyway, so the thing is that if you have some middle eigenvalue conditions, this is satisfied, and for now word things, so this C may depend on this HI here. So this C may go to 1 as you go to. So if this is MPNC, then then the final part is that you'll have this kind of decomposition of the transverse structure. So this will be a join, and then this HI will be the Zariski closure of unipotent Lie group. So this is our because of this previous work, this will be diagonalizable, and then Q will be acting trivially here. And point is that so if you have any elements like this, and if you have any largest norm eigenvalue associated with this some point, then this point will always converge to some point in the interior or of this, or but the point is that the direction may converge to here, but one of these, but it may not really converge. Okay, so one of these. But the point is that if you in this situation, this direction, if you choose a point in this direction, it will be affiliated with this largest norm of eigenvalue. Okay, it may not be the eigenvalue, but it will be affiliated in the direction here. So if you choose a point in this largest norm direction, okay, so that's why you can show this inequality. Okay, so that's the end here. So we end this lecture here today.